Okay, so I'm making this recorded lecture because we have missed couple of classes because of the vacation and other things. Basically, whatever we can cover here, I will cover some of the portion from this lecture too. Just the last portion. I think some of the portion I have already covered in the class, but the last portion, which is mostly conceptual, I'll try to explain here. And if you have any confusion, obviously we can discuss that later on in the class. So let us try to start. So I think where we should start is with the concept of logic level. So I think briefly we discussed about the concept of logic levels, why that is needed in representing um, uh, binary labels in logic gates. So what we actually finally decided upon was that generally for any kind of logic gates, two states we have. So logic 1 and logic 0, to represent them we use this approach of logic level. So here you see it's written logic levels refer to defined voltage ranges that represent binary states in digital circuit. Okay, so binary states, basically to represent them we use logic levels. So we first of all discussed about just taking a threshold to distinguish between logic 1 and logic 0 for representing using a voltage level, but how that is not a very good idea. Then we decided upon this particular method. So in logic levels what we do, if we have like voltage levels like what let us say 0 volt to 5 volt, this is the amount of voltage we have to represent these two states, logic 0 and logic 1, high and low, right? So what we do is basically we take a range of voltages to represent both of them. Okay, so let's say for logic 1 high, maybe we can just use this amount of voltages 5 up to, maybe, I am just giving one example, maybe up to 4 volt. This amount of region will be reserved for representing logic 1 basically, and same goes for logic 0, we do that. Okay, so some amount of region we take for representing these two states and then in between them we also keep a portion that is actually forbidden. Okay, so let us take maybe red color, that will be this. So this portion is actually forbidden, and if any voltage in that region comes in our logic gates as input or as output, basically we will ignore that. That is not acceptable, that is not valid. That is the idea. So this is kind of like undefined or not permissible region basically. So this is how we represent in logic levels, right? And also we saw that like this is not just one particular statement or one particular set of rules that is both valid for inputs and outputs. So we specifically choose these ranges separately for outputs and inputs of logic gates. That is the idea. Okay, so as we have seen here, like we have discussed here, this amount of region is selected for representing logic 1 and this is for logic 0, but it can be and it will be different for representing output and input. So these ranges will be different. That is what we are going to see right now. Okay. So let us look at this figure first of all, maybe that will be easier to understand. So here, as you can see, we are just taking this figure to explain how these voltage ranges in logic levels are actually defined. Okay, so these two are logic gates of same logic family, so that means whatever rules we can apply at the output of this one or input of this one, same can be applied for this one and this one, no problem. So basically we just connected two together so that we can explain both of the logic levels, one defined for the inputs, one defined for the outputs, right? So basically, if we just first of all look at the output of this particular gate, okay, so this one, so here, so how we represent this logic level is we will take the highest possible voltage and the lowest possible voltage, which is probably 5 volt and 0 volt. In that region, a particular portion will be defined for representing logic 1 and another one will be used for logic 0. The idea is we also define two term called VOH or sometimes VOH minimum and another one VOL or sometimes VOL maximum. So what is VOH? So basically, when a designer is designing a logic family or a gate, a logic gate based on a logic family, this particular logic gate has to follow some rules. So these rules are part of this logic level rules basically. So what is that? So they say that if this particular gate is trying to output logic high or logic 1, it should at least give this amount of voltage. Okay, it can give 5 volt, a slightly less than 5 volt, no problem, but it can never be less than this boundary we see here or this line we see here. This line or the minimum voltage that it has to show at the output if it wants to actually output logic high, this is called VOH. And because this is the minimum possible voltage or minimum permissible voltage for that, that's why we are also adding a minimum at the bracket, right? So sometimes you will see this minimum is here, sometimes it's not, but this is the actual term here, right? And these are the rules this particular gate must follow. Okay, so you will see that whenever we actually look at any logic gate, we get data sheets from internet for that logic gate based on a specific logic family if that is built, and in that logic in that data sheet you will see all these rules and all these parameters it follows characteristics are actually written here. So there it will be specifically written that it will be written that what is the value of VOH for that gate. So it can be, let's say, 4.2 volt. That means whenever it is trying to output a logic high signal at the output, it must obey that the voltage will never be less than 4.2. It can be 4.5, 4.6 based on the loading condition, based on the amount of gates connected at the output. It can vary, but it can never go less than 4.2. That is the idea, and that will be basically VOH. And similarly, this same concept can be explained for low signal as well. So for low signal, we know this is the amount of region which is permissible, right? If it wants to output logic 0, then it has to be within this region, but it can never go above this line. That is the idea. And this line or this particular voltage basically defined for this logic family will be VOL. Okay, VOL, and this maximum is written here because this is the maximum value is allowed for this output. It can never go beyond that. That is the idea. Okay, so just try to understand, because we are talking about output, that's why O, and this parameter is actually defined for the high condition, that's why H, and same goes for this one, you see, in this way. Now this is for the output of this logic gate, but whenever we are talking about the input is not controlled by this logic gate, right? If I talk about this one or this one, the input is not controlled by this one. Input will be coming from anywhere else. We can provide that, and based on that, this logic gate will behave. It can output logic 1 or 0 based on the input. But what voltage should be provided, what are the permissible voltage to be inputted here, will be decided by another definition of logic level, right? So this is here. So basically they are saying for this particular logic family, we don't know which logic family that is, but this is the valid region or valid amount of voltage we can provide at the input here to make it recognize it as logic 1. So if I provide from 5 volt up to this line, this is the minimum voltage. In this region, any voltage if given to this logic gate, it will recognize this as a valid logic 1 signal, and based on that it will output any value, right? So that the minimum value we should provide, we can never go below that. If I want to provide logic high, this amount is called VIH, right? So this is actually kind of like instruction to use this device, use this logic gate, and if you want to actually input logic high signal, you have to obey this rule. So you can give any voltage within this region, but you can never go beyond VIH. Okay, and same goes for the low signal as well. So for low signal as well, this is the permissible region, but you can never go beyond this line here, and this is the maximum voltage you can provide if you want to make this logic gate recognize the signal as 0. That's the idea. Okay, so here also look at I means we are talking about input, I means H means high, L means low. That's how we can recognize. And also minimum and maximum, I guess you understand, that's why we have at the bracket, but sometimes you will see this minimum and maximum in the bracket is not actually written. Okay, so if we understand this much, the idea of logic levels, which is defined separately both for the output and input for a specific logic family, now we can talk about noise margin. This is another advantage of using this concept of logic level. So what is noise margin? The idea is like whenever any signal is going from this gate to that gate, this is the most simplified version of representation. That's why just a wire here is given. So there can be many things here, many complicated things here in between these two gates, and at that condition what can happen, any kind of noise can actually fluctuate, and any kind of noise can actually change the signal you are actually sending from here. That's the idea. So if you're let's say providing maybe just outputting 4.2 volt from the output, maybe because of some noise it has degraded to 3.8 volt maybe, and that 3.8 volt we are getting here. Understand? That is the idea. So this can happen in between this transmission. Any voltage can be dropped or any noise can be added. That is the idea. And if that happens, how the receiving side will properly recognize that? That is the idea. So that's why we have separate logic levels actually. So let's say the minimum condition or the worst possible condition we have for a logic gate, if it is trying to provide logic high, let's say. So let's say this particular gate is trying to output a logic high, and because of some reason maybe it is providing the least or worst possible voltage for logic high, which is what? This one, right? This is the minimum voltage that must be shown here to be recognized as logic 1. That is the rule. So let's say if this particular gate is actually outputting VOH, and because of some noise here it can drop to a certain lower value. That can happen. So if that happens, then what will happen? It will drop like that. And if it drops like that, still you will see, if it's not so much low or so much noise is not being added here, maybe still it will reach here whenever we reach the input of the next gate. Understand? Still it will be recognized as valid high signal by the next gate. That is the idea. So this is happening because we have this gap between the two values VOH and VIH, we have this gap here. This is called the noise margin. So this means this amount of noise can be tolerated by the system because this is this amount of voltage higher than this amount of voltage, right? So that's fine. So this is called noise margin. So whenever from the output a signal is coming, any noise can be there and still it will be tolerated by the input because of this amount of voltage gap between the two definitions. Same goes for this one. If maybe we are trying to output a logic 0 and we are actually outputting this value here, because of some noise it can also increase in voltage. If that happens, maybe it will go like that, but still it will be recognized by the input of the next gate. That is the idea here. So if this length here is higher than the one we are seeing here, obviously noise margin will be higher. That means it can withstand or tolerate more noise then. That's the idea. And we are calling that noise margin, and we have two different name for that. For the high portion we call that VNH, high level noise margin, and this one VNL, low level noise margin. Okay, and you will see that these two values can be exactly same for some of the logic families, and sometimes it may also happen that the values are not same. Maybe one noise margin is higher than the other one. Then actually whenever we actually define the noise margin for that logic family, we take the lower value. Okay, so that is what you have to understand. I think it's written here, if the two values are different, then noise margin is taken as the lower of the two. So how we can actually calculate the noise margin? Like for this one, VNH is actually what? VOH minus VIH, right? And VNL is equal to VIL minus VOL, because this is higher, that's why we have taken it at the front. Okay, so this is how we can calculate. Okay, then like this characteristics parameter, we have learned about 4 parameters: VOH, VOL, VIH, and VIL. There are other certain parameters, characteristics parameters, which define how good or how bad a logic family is. Okay, so we will talk about those as well. I mean, whenever we look at a datasheet, I mean, to understand whether a particular device is good for us. Okay, so what we do, we look at the data sheet of a particular device. All the characteristic electrical parameters are written here. What is the temperature, what is the maximum temperature it can withstand, and similar things like that. So these are certain kind of parameters, and to measure the quality of a particular device, we can look at those parameters basically. Okay, so like that, like these 4, some other parameters are this one, right? Based on current. So high level input current, IIH, what is that? Okay, so basically the idea is also we have to think about the current that flows into a particular gate or come out of a gate, both in terms of input and output. Okay, so there are certain parameters like that. So what we are saying here for the first one, high level input current, this one, okay, high level input current, I. So we are talking about input current. So the idea is, let's say I'll just take one example, maybe here. So this particular gate is connected here with the input of this one. So the idea is whenever it is getting high signal at the input, what is the maximum current it can draw? That means it can go inside or go from it to outside. both can happen. We will see that based on the architecture, it can vary, but for most of the common architectures like TTL, you will see that whenever we are trying to provide a logic high from the previous gate to this one as input, current will go inside like we can see here. But our question is, what is the maximum amount of current that can flow? And that amount is actually what we are seeing here, IIH, or high level input current, IIH. Okay, but you have to understand, we know from the concept of logic levels, to give here logic high, we can provide any amount of voltages. If I just follow the requirement, if we can follow the requirement, I can give any range of voltages starting from 5 volt to the minimum voltage, which is VOH. If you remember, I can again go back, just try to remember that. Like, I think we have discussed here, like for this one, we can provide any voltage, or any voltage is permissible within this region, but we can never go beyond that. For this gate to behave properly, it should output any value from 5 volt up to VOH. VOH is the minimum voltage, right? But you have to understand, like in this particular circuit we are seeing here, whether you give 5 volt or VOH or any value within that region, based on that voltage, current will vary through this path. Current may increase or decrease, right? So we cannot just say if we provide logic high, then what is the maximum current? That is not complete. We have to take a specific voltage, and based on that voltage, what is the maximum current it can draw, it can intake, that we have to define. That will be a specific parameter we can use in the datasheet, right? So that voltage we actually take as VOH. Why is that? The idea is whatever current will be going into this input to this gate will be provided by this gate, right? Like all the gates we are seeing here, these are connected with this gate, and all the current going through inside of these gates are coming from this first stage gate, right? So that means we have to understand what is the capability of this gate, whether we are exceeding that. So we have to think considering the situation of this gate. That's why we are taking the lowest voltage, because in the lowest voltage, if let's say if this is providing VOH and we are getting that at this stage for all of the gates here at the input, they are getting VOH. That means if anything happens, if anything bad happens, if any high amount of current is drawn by these gates, it can affect VOH and it can drop lower than that. VOH is the minimum voltage it has to provide. If it goes lower than that, that will invalidate its property, right? So that's the thing. So we are checking it at its most vulnerable situation. So why that happens? So just try to understand like why it may happen that if it is providing the lowest possible voltage for representing logic 1, and if high amount of current is drawing from there to these gates, what bad can actually happen? So if you understand like how electrical circuit works, let's say I am just drawing a very simple circuit which representing how from substation the electricity is coming to our household. Okay, so maybe this is just one representation of that kind of substation, and then with a very long line from that substation to our home or to our particular area, this electricity is coming, and we can represent the transmission line using this, maybe this resistor. Okay, let us call that R. And then maybe just to represent our home maybe. Okay, so we can use one load. So we are just drawing power, right? So maybe this is that, a kind of like a resistor. I am using the most simplistic explanation, but basically it is drawing current, right? So that current is coming from here, from the substation. The idea is whatever current is flowing inside of our household, that current should also go through this transmission line, and because of that, I multiplied with R, this amount of voltage will be dropped through the transmission line. So if the substation is generating Vx amount of voltage, are we going to get that Vx amount of voltage at our household? Obviously not. There will be some amount of voltage drop, which is IR. So what we are going to get is maybe Vx dash is equal to Vx minus IR, the transmission loss, right? So if something happens like maybe in our particular area, multiple more households are connected now with the same substation, maybe something like that. I can just remove this portion maybe again, and now maybe we have multiple more houses here connected. They are also drawing power from the substation. Now obviously previously whatever current we were taking, we were consuming, it will be higher than that now, because we have three different household appliances or house. So basically they will draw more power, more current. So this will increase, and if this increases, so will this IR drop, right? So if voltage drop increases here, that means at this point, at the receiving end, we are not going to get the voltage we would get earlier, right? Because we are drawing more power, more amount of voltage is being dropped at the transmission line. So this particular concept or this particular phenomenon is actually called loading effect, right? And same concept can be applied here as well. If you think about logic gates, the same concept can be applied there as well. So how is that? Like here, this whole logic gate is built using different circuits. There can be resistors, capacitors, and many such things. And whenever some amount of current is being drawn at the output, that amount of current is also flowing through those resistors, and there will be some voltage drop. And after those voltage drops, whatever voltage is remaining, that we get at the output. That means more amount of current if flowing, that will drop more voltages inside of the gate, and at the output we will get less than the amount we got earlier. That is the idea. So that means if currently we are providing VOH amount of voltage, and if like right now maybe 10 gates are connected, this is the maximum amount of current it can provide maybe, and still hold VOH voltage. If I increase the amount of gate here to 20 gates are connected with this gate at the output, what will happen? Maybe it cannot provide now the amount of current these gates needs. So what will happen? If 20 gates are connected here, more amount of current will be required, that will be consumed from here, that will reduce the amount of voltage we will get at the output, that may go less than VOH, and that will actually cause problem. Understand? So this is how we actually define those. So that's why basically that's why we are defining IIH using VOH. So whenever, if I just let's say connect two gates here, okay, so just I am showing two gates. The idea is we are going to measure IIH, that current here, which is the maximum current that this particular gate can consume if it is getting logic high. But for that logic high, the amount of voltage it will get is VOH. Okay, so the previous gate is actually currently providing VOH voltage, and in that case, what is the maximum current it can consume? That will be the value of IIH. And similar concept similarly can be explained for IIL as well. Just now only difference is now we are talking about low condition. So that means this one will be VOL, right? And here obviously we are going to call that what, IIL, right? So idea is, what is the amount of current consumed or maybe coming out of that. We will talk about that later on, but some amount of current is going whenever we are providing VOL amount of voltage from the previous stage, or just this is getting VOL, then what is the maximum current it will intake, or maybe same amount of current may also go out. So you see this thing is actually written here. For this one, current is flowing into the input, direction is that. And for this one, whenever low condition, current is actually going out. Why is that? Whenever we will talk about specifically about the architectures of different logic families, you will see how that actually happens. So whenever for a gate, let's say for example, if I talk about TTL logic families, for a gate you will see whenever we are providing 5 volt, any high voltage like that, current is actually going inside. The architecture is making that happen. But whenever we are giving a value close to 0 volt, maybe like that, you will see that this direction has changed to like this. And also the amount of current also drastically vary. So if I talk about like in standard cases, what happens, you will see that whenever current is going inside, or this in this high condition, this value for TTL is 40 microampere. Okay, the maximum current flows inside whenever we are providing VOH voltage, right? This is, but for this one, whenever current is going out for low condition, this amount of current is this one. So why that happens, whenever we will see that, look at the architecture, you will understand, basically because of some diode, right? Okay, so that's the idea. So also another term you may actually learn here, which is called unit load. Okay, so sometimes defined in terms of unit load. The maximum value, this value, we call that 1 unit load, kind of like that. So for high condition IIH, that value is 40 microampere for TTL logic family, and same thing for this one. The unit load is actually 1.6 milliampere. This amount of current actually flows out for one gate. This is the maximum amount of current flows whenever we are providing a logic low condition. I hope you understand. Yeah. Now same idea, same thing what we have discussed, just this is for the case of output. So this whatever we talked about earlier, this was for the case of input, but what will happen if we talk about the output? Okay, that's the idea. So like here, whatever current is going into these inputs are coming from the output of these gates, right? So there should be also some maximum value it can provide. So that is also defined like that. So whenever, basically whenever we have given proper input such that the output is currently showing logic high, okay, and at that condition, what is the maximum amount of current it can actually provide? That's the idea. So that will be called what? IOH. Okay, this is IOH, this one. And also for this one, even though this is not written here, the voltage we actually take, like what should be the voltage at that condition? VOH actually. I mean, whenever the output is exactly outputting VOH, at that moment, what is the maximum amount of current it can provide until it behaves abruptly. So if this is the maximum value of current it can provide, if somehow more amount of current is drawn, it will violate its property, and maybe this VOH will go lower than that. Understand? So yeah, same goes for this particular one. So IOL, same concept, just for logic low, logic 0 condition. So in that case, obviously the voltage should be what? VOL. and we will call that IOL, the maximum amount of current it can provide at that moment. Actually, again here also you will see that current direction is different. Whenever we have high voltage here, current will go in this direction, and whenever the voltage is low here, logic low, then current will go in this direction. This is how it works. And also for all of the gates we have a specific rule of direction, that is, for a gate, whether that be input pin or output pin, if current is going inside of that pin, that current magnitude is considered positive, and if current is going out of that pin, we take that value, that current value, as negative. That's the idea. Okay, now let us look at some next characteristics parameters. These are simpler than previous one. So what is supply current? ICC. So whenever you have used like this kind of logic ICs in your lab, so you have seen maybe in each of the ICs we have 4 different gates. Maybe if that is quad NOT gate, there should be 4 NOT gates inside, and with that also we had 2 pins like that. Here we provided VCC, and here we provided ground, right? So actually how we calculate this supply current is calculating how much current is actually going inside of VCC. Okay, so that's how we actually calculate. And for this current, if this is ICC, actually it is providing 4 gates at a time, 4 gates at the same time. So if you want to find out what is the amount of current consumed per gate, that will be ICC divided by 4 basically. I mean, I should not actually write like that. ICC is actually for per gate. So if I talk about this one, maybe 4 multiplied with ICC will go inside of that. But if you want to find out what each of the gate is actually consuming, you have to take 1/4 of that. That's the idea. Okay. Now rise time. What is rise time? So this is generalized concept. This is not specifically for this particular lecture. Rise time and fall time are mostly used for electronics. So idea is any kind of pulse signals. It can go from low to high like that, or also sometimes high to low, right? So the idea is how steep is that we can calculate. Based on that, how accurate, how good a signal can be measured. So the idea is rise time is we calculate whenever like for this one, I think I should draw it a little bit better than this one. So rise time is whenever a signal is going from low to high, and basically how much time it takes to go from this low to high. To calculate that, what we do, definitely we take whenever the signal actually reaches 10%, and also we take another point whenever the signal reaches 90%. We take the time difference between these two, and we call that rise time. And similarly for fall time, same thing, we take a point which is 90% of the signal, another one 10% of the signal. We take the exact time of both of them, and then take the time difference between these two, how much time it takes to go from there to here. That's the idea. So these two things. Then propagation delay. So what is propagation delay? Maybe using this particular figure it will be easier to understand. So propagation delay, in a simpler term, what it is if I talk about a gate like this one, a simple gate, whenever you provide a signal 1 or 0, something like that, to actually reflect that input to the output, it may take some time. So if maybe it was previously 0, and that means the output is currently 1, if I suddenly now change it to 1, output should also change to 0, right? But it doesn't instantaneously change. it takes some time. So whatever signal you have provided at the input, to propagate that and at the output to reflect that, it takes some time. So using this figure, actually you can understand, like you don't have to, like if you want, you can just omit this portion for now. Okay, so we can just don't think about that, then try to understand. So basically, let's say maybe for a particular gate, this is the input and this is the output. That because you see this is going from low to high, and because there will be some delay, after some delay that input is being reflected at the output. This is basically a buffer. Same thing is happening at the output, but it is taking some time. This is the propagation delay. And same thing we can also discuss in terms of if that was a NOT gate. So previously we talked about if that was a buffer, but same thing similarly again explained here, if that was a NOT gate. So in that case we can omit the middle graph, but these two you can just compare. So if I have given this signal at the input, at the output we are going to get this signal, but it will take some delay. That's the idea, and that delay is calculated like that. And how we calculate? We take same point for both of the cases. Okay, so we have taken 50% signal point here for the input, 50% signal for this one as well, and then we take the difference of time between them, then we calculate. But we actually have two different parameters. One of them is for low to high, another for high to low. You see LH and this is HL. So how is that? We just have to look at the output. So if in this propagation delay the output is changing from low to high, then it will be called TP-LH. And if the output signal is going from high to low, we are going to call that TP-HL. And same goes for, you see here also same thing is happening, if you understand. So anything can happen to the input, but we will just look at the output. If it is going from low to high, we are going to use this particular notation. Okay, so the same thing is explained here, I guess. Next one, maximum clock frequency. So what is maximum clock frequency? Probably we have learned about flip-flops, right? So maybe I can draw a very simple flip-flop, D flip-flop, right? DQ, and here we can use a clock, and this is called Q bar actually. Yeah, right, something like that. So the idea was any value can be here at the input, but it will only go at the output if we have given clock pulse here, right? So clock pulse will be something like that. But the idea is, what is the maximum frequency you can use here for the clock? That is the idea, because obviously there will be some propagation delay for a signal to go from this D to Q. And if that propagation delay is larger than this clock pulses, then obviously it will not work, because then it will take some delay. That's the idea. So that's how we calculate the maximum clock frequency. That means the maximum clock frequency we can use here so that it will not behave abruptly. Okay, now power dissipation. So power dissipation is basically how we calculate power, multiplication of voltage and current, same. So we have discussed about one of the situation here, maybe I think I drawn where is that? I think I drawn it here somewhere. Yeah, no, maybe I can draw it again. So I had drawn something like this. So the logic gates we use, right? This one. So we saw that there was a VCC and ground pin, right? So basically the voltage we provided generally was 5 volt, but with that also some amount of current can also go through this path, so which was actually ICC, right? So we just multiply these two, ICC and VCC, that will be the power dissipation for a particular logic IC, and it can also be calculated in terms of a logic gate. If there is 4 logic gates in this logic IC, then we just have to divide that by 4. That is the idea. But sometimes the problem is this value here, ICC, this amount of current consumption can vary based on the state our logic gate is in. So either that can be in high condition, either that can be in low condition, and based on that two different amount of current can be consumed. So these are called ICCL and ICCH. What we do, we actually calculate for both of the cases. For once we make all of the gates high, then measure the current, that will be ICCH, and then we make all the gates low, then we get I can write it here, ICCL. So we just add them together, then divide it by 2, and then this is the amount of current, basically multiply that with VCC, that will be the power consumed by the device actually. Then if you want to find out the power consumption per gate, that will be this value divided by 4. Okay, now we are almost there. Speed power product. So one of the thing is whenever we try to build a gate, our desire is to reduce the amount of power consumption as much as possible, also make it as fast as possible. But the issue is, if you want to make it fast, that also consumes more power. So we will see that. I mean, whenever we practically look at architectures, we will see that if I want to make a particular gate work in higher frequency, that will take more power to make it work. So that's the idea. So kind of like a trade-off. And so because of that, for a particular product, the speed power product gives us the idea how much efficient that is. Okay, so if you want to increase one, another should be reduced, something like that. Understand? So we also have a particular speed power product value which is expressed in picojoules. Okay, so what we do, we calculate the propagation delay of our device, which will be calculated in terms of nanosecond, and also we have to calculate the power dissipation per gate, that will be measured in milliwatt. And then what we do, we just multiply these two. So this is actually in 10 inverse 3 level, and this is in 10 inverse 9 level. So if you multiply these two, this is pico, so 10 inverse 12 level picos. Okay, so this is how we calculate. Okay, so last, fan out and fan in. So the concept of current consumption, what is the maximum current a particular gate can provide at the output, what is the maximum amount of current a gate can take as input, these are actually coming from this particular two concept, fan out and fan in. So fan out is the number of inputs a logic function, number of inputs of a logic function that can be driven from a single output without causing any false output. So this is kind of situation. So in this particular gate at the output, how many gates you can connect, provided that still it will behave properly. So the idea is, let's say if the if it is trying to provide logic high and the voltage it's providing is VOH, how many gates you can connect here, still it will provide VOH, and it will not go less than that. That's the idea. Okay, so that is fan out of this particular gate. So how we can calculate? We can simply calculate using this formula, IOL divided by IIL, or IOH divided by IIH. So why is that? This one is the maximum amount of current gate can provide whenever it is trying to provide high signal, and this is the amount of current a particular gate consumes whenever it is getting high signal. So if you divide this current by this current, you will understand how many gates you can connect, and still it will behave properly. And same goes for this one, same concept, but just for logic low condition. Okay, and fan in is for a particular gate how many inputs there can be. So based on the number of inputs of a gate, you can easily calculate the fan in. Like here, the number of fan in is M. Okay, very simple to understand. So these are just some of the concepts we had to understand, and over and over again, whenever we will talk about different architectures, you will see that we will try to judge a particular logic family based on this characteristics parameters. That's the idea. And also there will be some mathematical problems, very simple, based on these concepts. Like maybe you will have to calculate a speed power product of a specific logic family. Maybe you will be given different values, like what is the voltage, what is the current consumption, something like that. So not that difficult. I am planning to give you one assignment based on that. There will be some problems related to these concepts here, mathematical problems. You can solve them, and then also we can discuss those. If you have any problem in the class, we can discuss about the problems. Okay, so that's all for this lecture. Thank you.